In this problem, we're going to use a differential equation approach to find I of t for t greater than 0. We've got a circuit with an inductor. We have one switch that's going to open at t equals 0. Because we have DC sources, our response is going to be I of t is equal to K1 plus K2 e to the minus t over tau. And of course our task is to find values for K1, K2, and tau. And to start, let's look at the circuit at t equals 0 minus so that we can calculate our initial conditions. Here's our circuit at t equals 0 minus. Remember, we assume that the circuits in steady state, so our inductor is replaced by a short circuit. So if we look now, the voltage across our resistor is 0, so that means the current through here is 0. And if we look at other elements in the circuit, for instance, if I apply KVL around this loop, that has to be 12 volts across that 2 kilo ohm resistor. And also, applying KVL around this loop means that there's 6 volts across that resistor. Now, as a result, that says there's 6 milliamps of current in that direction. There's 2 milliamps of current in that direction. So if I apply KCL, that says the current in that direction has to be 4. And if I apply KCL again, that says that this current is 4. So then I of 0 minus equals I of 0 plus equals 4 milliamps. Remember, this is continuity of current for our inductor, so when the switch moves, that current can't change in 0 time. Now, let's look at the circuit at t greater than 0. So now the switch is open. Here's our circuit. Let's take and define a reference node, and we'll have we've basically got a 2-node circuit. I'm going to define this voltage as V of t, and we've got really 3 nodes. We've got 2 node voltages. Here's one, but it's known. So now let's apply KCL to this top node. So we'll have V of t over 2K plus V of t plus 6 over 3K plus I of t equal to 0. Now, working on this equation some, we can collect terms. For instance, we'll have 1 over 2K plus 1 over 3K times V of t. This term here is a 6 over 3K. That's 2 milliamps. We can move it over to the other side. It'll become minus 2 milliamps, and we're left with an I of t term. Now, we've got one equation and 2 unknowns. We know, for instance, that V of t is equal to 6 times 10 to the minus 3 times di dt. So now let's substitute that in for here. Okay, so we'll get 1 over 1.2K times 6 millihenries times di dt plus I of t is equal to minus 2 milliamps. And we get 5 times 10 to the minus 6 di dt plus I of t is equal to minus 2 milliamps. And if we divide through by the 5 times 10 to the minus 6, we can get di dt plus 2 times 10 to the 5th I of t is equal to minus 400. So here's our differential equation. Now what we're going to do is we're going to substitute our response in, or the form of our response. We know that I of t is k1 plus k2 e to the minus t over tau. So now let's substitute in. We have di dt k1 plus k2 e to the minus t over tau plus 2 times 10 to the 5th times k1 plus k2 e to the minus t over tau, and that's equal to minus 400. So if we look, we'll have minus 1 over tau k2 e to the minus t over tau plus 2 times 10 to the 5th k1 plus 2 times 10 to the 5th k2 e to the minus t over tau is equal to minus 400. And if we look, for instance, 2 times 10 to the 5th k1 has to equal minus 400. So that says that k1 has to equal minus 2 milliamps. And that's equating these two terms. And then if we look, we have minus 1 over tau k2 e to the minus t over tau plus 2 times 10 to the 5th k2 e to the minus t over tau has to equal 0. For instance, the k2 terms cancel out, e to the minus t's cancel out, and we get 1 over tau is 2 times 10 to the 5th, and that gives us that tau is equal to 5 microseconds. Now, we're still not quite home. We know that I of t is minus 2 plus k2 e to the minus t divided by 5 times 10 to the minus 6 milliamps. And we use our initial condition now. I0 minus equals I0 plus is equal to 4 milliamps. And that's minus 2 milliamps plus K2. So it says K2 is equal to 6 milliamps. So I of t minus 2 plus 6 e to the minus t divided by 5 times 10 to the minus 6 milliamps. Now let's plot it. So if we look at our current, and this is in currents, we're going to scale it in milliamps. It starts off at 4. Final value is going to be minus 2. So it's going to do something like this. And it turns out that where it crosses 0, the time is 5.49 microseconds. And you can solve for that by setting that equal to 0.